Hello, ladies, gentlemen, and in between, and welcome back to another episode of Maths with Hamblin with your beautiful host, Hamblin. And today, my boys, very simple, we're just going to be continuing on with what we did last episode, which was function transformations, and we're going to finish off with just a little bit of harder concepts and stuff. It's going to be nice. Without further ado, let's go. Okay, so the first thing I'd like to cover in this episode is just a little recap of last episode and something that I forgot to talk about last episode. So to introduce this concept, let's just imagine we've got y equals, so we've got the graph of just some random general function, and we're going to transform that graph by taking y equals f of x plus 3 and then minus 1. So we're adding 3 to each input before putting it in the function, and then we're going to subtract 1 from each of those outputs. Now, as you learned from last episode, this has the effect of shifting the function 3 units to the left, and then shifting it down by 1. That's called a translation, by the way. That's what that's called when you just move something about. That's called a translation. As you can see here, so we're basically just moving everything to the left by 3 and down 1. And the reason I'm bringing this up is because sometimes exam questions will love to say that the graph of a function is translated by vector, like 2, 3, or something like that. And essentially what that means is, you see how this is kind of a vector here, and it's got a component here of -3 and then -1. So what you could say is that everything on this function is being translated, is being moved along that vector. Moved -3 and then -1. So it's effectively just going diagonally down like that. So that's what that means. It's being translated by that vector. So if a question asks you something like, find the equation of, like, a graph is translated by vector -3, -1, you need to think to yourself, okay, that shifts it to the left 3 units and down 1. You need to think what graph transformation that corresponds to. And then if it wants you to find the equation of the new graph, then you need to do that business. In fact, I'll give you an example real quick. For example, if you had the function y equals 1 over x, and the question told you it's translated by vector -3, -1, you think, well, shifting to the left by 3, going down by 1, that corresponds to this translation up here, in fact. And what that will do, okay, let's find the equation. So first of all, we need to add 3 to the input to shift the graph along 3 units. So in other words, we need to take the input x and add 3 to it before putting it in the function, and then to the output we need to subtract 1. Boom. And there you go. That's the new equation of the graph. Beautiful. And if you don't believe me, go to Desmos, put this in, and you'll see that they're nice translations of each other. Anyway, sorry for that side note. Quickly moving on to our first new function transformation. Okay, so the function transformations that we've considered so far just involve translation and adding to the input and the output before we put it in the function. But for these next ones, they involve multiplying by a number, what's called scaling, and you'll see why it scales, actually. So, the first one we're going to consider is if you have the graph of some general function, f of x, and then you transform it by taking the output of the function and multiplying it by some number. So, for every single input x, you put it through the function, and then you have to multiply it by some constant a. It could be positive or negative, whatever. Now, let's think about what effects that might have on the graph. So, let's consider a bunch of these inputs and outputs. For example, this input here has an output like skadoom. Now let's assume we're multiplying by a positive number to start with. So if we multiply by a positive number, let's say bigger than 1, it's going to multiply that output and it's going to make it a lot bigger. So it's going to send the output flying to up here. And let's say we consider this input here. The output is negative. So if we multiply by a positive number, because we're multiplying by a positive number and it's bigger than 1, it's going to make the negative number more negative, so it's going to shoom it all the way down to here. Similarly, with this input, positive output, multiplied by a big number, boom, shadoom. Now what you might be able to see here is we've kind of got a stretched out version of the function, and that's exactly what this transformation does. It stretches the function along the y-axis, it scales it by exactly this number a. And if your number a was negative, then let's think about what that would do. If I just rub all the stuff I've already done on. Let's go through the same inputs and outputs again, but think of a as a negative number. So let's take this out. This input outputs that height on the y-axis. Now if we multiply by a negative number, it's going to turn this positive output to a negative output, so it's going to flip it all the way down to here. Now let's take a look at this input here. Output's a negative number, and if we multiply a negative by a negative, then we're going to get a positive number, so it flips it up again. And I'm sure you can see the pattern here. Multiplying by a negative number stretches the function and then flips it. It's pretty cool, right? And that is why, in fact, you might have wondered why, that is why x squared graphs, when they have a positive number in front of x squared, go like that, but when you make it negative, it flips it. It's because of this function transformation. So there you go. That's pretty cool, right? So yeah, and also, one last thing to note. If your number you're multiplying is less than 1, or multiplying by less than 1 scales down stuff. So if you multiply by a number less than 1, it's going to squish the function. Anyway, so to recap everything we've done, if you have a function transformation where all you're doing is multiplying every output of the function by a number, it scales the function along the y-axis. So that's pretty neat, and that's pretty easy function transformation. And yeah, there's nothing else to it. There's no crazy stuff like translation by vector or whatever. It's just what it says on the tin, which is really nice. For example, what they might say though is, for example, if you have, let's go to y equals 1 over x again. They might say the graph of y equals 1 over x is scaled along the y-axis by a factor of 3. So what that means is that it's basically it's scaled by a factor of 3. It's multiplied by 3. So that corresponds to a function transformation to 3 times 1 over x, or just 3 over x, which would be the new graph, which would look like if you stretched it out like that. Anyway, so on to the next one. Okay, so we finally reached it, the final boss of function transformations. This, what I'm about to show you, is definitely the hardest one that exists. And it goes like this. The function transformation goes from, you take your original function, and before you put any of your inputs x into the function, you multiply those inputs by a number and then put them into the function. And that happens for every input. And we've got to try and figure out what that will do to the function. Now, if you remember from the last video, I came up with this useful little tip that if you have a transformation affecting the inputs of a function, it affects along the x-axis, because the x-axis is where the inputs come from. And, for example, multiplying the input by a number. But if you have something that only affects the outputs, for example, f of x plus a, then that only affects stuff along the y-axis. And this is a similar story. So let's, I'm going to choose a specific example again. Let's choose a nice friendly x squared graph. So let's say we go to y equals x squared, and let's say we transform that to y equals a times x squared. And we've got to figure out what that is. And I'm actually going to make a specific number. I'm going to make it equal to 2. Because you'll notice I quite like 2. It's quite a nice number. It's the only prime number that's even, in fact. It's quite interesting. Anyway, so let's figure out what this will do to the function. So I'm going to graph a nice little x squared. Ooh. This is just our normal friendly x squared. So 1 outputs 1, 2 outputs 4, and so on. Very nice and easy. Now, let's consider the graph of y equals 2x all squared. Draw a new nice graph. Right, so now let's consider the input 1. Now, when we put it into the function, it's going to get multiplied by 2, becomes 2, and is now 4. When the output is now 4, which now goes to vroom. We plot that way. And let's consider 2. You plug in 2 to that function, it's going to come 4, you square it, you get 16, which is going to be like way up here, so I'm just going to put it like as high as I can up there, hope you can see that. Right, now let's consider negative 1. Negative 1 will be the same story as 1, which will be outputs of 4, and so will negative 2, and 0 will still be 0. Now let's connect the lines and see what's happened. Oof, I haven't really drawn it amazingly well, I'm not going to lie, but essentially what you can see is happening is that the output that used to be associated with 2 is now with 1, and the output that used to be associated with 4 is now with 2, because the x-axis has kind of been squished by 2. And what this has the effect of doing is compressing the function along the x-axis. Imagine I got my hand here and I squished it inwards, and it squishes it inwards by a factor of 2. Which is kind of weird, right? Because if you multiply something, you'd expect it to get bigger, not to be compressed smaller. Which is just slightly interesting, isn't it? Now, let's consider the alternative cases. For example, what if your number was less than 1, like it was 0.5? Well, as you can probably predict, that would have the effect of stretching out the function. For example, the output that used to be associated with 2, now gets associated with 1, and you get kind of a stretched out effect. And if your number was negative, then that flips the outputs and the inputs, much like when we had y equals a times f of x, that's flipped on the y-axis. If a was negative, this will also flip the function, but horizontally. But in this case, it literally has no effect because x squared graphs are symmetrical. So, yeah. So, to recap all of the nonsense that I just said, I'm going to go without the pen for this one, solo, right? So, if you have a function transformation where it's y equals f of x to y equals a times f of x, so you're just multiplying all the outputs of the function by a constant, it stretches the function along the y-axis, and if it's negative, it will flip it over and stretch it. And if you have a function transformation that multiplies the input by a number a, this one, then that will they'll compress the function inwardly by a factor of a, so it multiplies the function down by a factor of a, and if that number happens to be negative, it will flip the function along the y-axis. Flip it like that, and also scale it by whatever the magnitude of a is. And that's about it for today's video. You might have to watch that a few times because that is kind of a confusing idea, but pretty much that's it for function transformations, and that's it for chapter 2. I can finally go on to geometry. So crazy, guys. Anyway, I'll see you in the next one. I really hope you enjoyed that video. Goodbye, my friends. Adios. Au revoir.